Hello, this is the 22nd video on my multivariable calculus. We are going to talk about triple integrals in spherical coordinates. So in the previous video, we talked about cylindrical coordinates, which is a coordinate system that is obtained from making polar coordinates three-dimensional. Here we're going to talk about another coordinate system called spherical coordinates, which can represent spheres and cones pretty easily. So here is spherical coordinates. So if we look at a point in three-dimensional space, so x, y, z, and a point P, there are three numbers that we assigned with this point P. The first one is the distance to the origin called rho. So that's the Greek letter rho. The second one is the angle between the positive z-axis and OP. And the third one is the same theta as in polar coordinates. So this is theta. So now we're going to find a relation between these three quantities and Cartesian coordinates. Okay, so if we drop the perpendicular and let's call that point H, we can see a relation here. So this angle right here is the same as phi because PH and the z-axis are parallel. So this angle is also phi. Looking at triangle OPH, we can say sine of phi is equal to opposite over hypotenuse. So that tells us R equals rho sine of phi. So that's one relation between spherical coordinates and cylindrical coordinates. The next thing we can do is we can write down x as r cosine of theta, and then substituting r by rho sine of phi, we get rho sine phi times cosine of theta. And then y equals r sine of theta, substituting by rho sine phi, we get rho sine phi sine theta. So these are the relations between x and y and spherical coordinates. If we drop a perpendicular from this point, we can say this guy is z. So looking at this right triangle right here, the adjacent, which is z, is equal to rho cosine of phi. And finally, the last relation is x squared plus y squared plus z squared is equal to the distance to the origin squared. So these 1, 2, 3, 4, and 5 relations. These 5 relations are really important to know when we are solving problems in spherical coordinates. Now, what are the limits of these quantities? If we look at the rho is the distance to the origin. So rho is greater than or equal to 0. What are the limits of phi? Well, the maximum value of phi is when we are in the opposite, in the positive z direction. So that's 0. That's the smallest value of phi. And the largest value is when we are exactly on the opposite end. So the angle that is maximum is going to be pi. And theta is on the xy plane, so the maximum and minimum are 0 to 2 pi. Okay, so now we will do some examples. The first example is identifying these shapes. We want to first understand how to deal with this new coordinate system, and then we will do examples, triple integrals in spherical coordinates. So what is rho equals 5? Rho equals 5. Rho equals 5 is all points that have distance of 5 to the origin. And what is that? This is the sphere of radius 5 centered at the origin. Now let's look at the next one. The next one is phi equals pi over 3. So what does it mean that the angle is pi over 3? So if we look at the angle phi, what we have is we want this angle to be a fixed angle. So this angle would have to be pi over 3. So what does that give us? So this angle would have to be pi over 3, and that means you can take this angle of pi over 3 and rotate it about the z-axis. So this is a cone. This is a cone with vertex at the origin 0, 0, 0 that opens up. Okay, so the next one is theta equals pi over 4. So if we look at the third one, we have all the points that theta is equal to pi over 4. So theta equals pi over 4 means this angle is pi over 4. So what are all the points that theta is pi over 4? So they are points that when you drop the perpendicular, you are at this ray through the origin. So what are these points? That gives you all of this half plane. So it could be also below this line. So this is a half plane. So that's the third one. And finally, the last one is theta equals pi over 2, which is a half plane, and phi equals pi over 3. So phi equals pi over 3 is a cone. Theta equals pi over 2 is a half plane. So we have theta equals pi over 2 is in fact the YZ plane. So that's theta equals pi over 2. Theta equals pi over 2 is this one. And then phi equals pi over 3 is a cone. So the intersection is the array through this. So it is that phi equals pi over 3. It is this one. So this is a ray on the YZ plane from the origin. So this helps us understand this coordinate system. So now we want to understand how to switch to spherical coordinate system. When we switch, we have a factor called spherical factor. So the factor is rho squared sine phi. So when we switch, we do rho squared sine phi. That's kind of like r in cylindrical coordinates, and then d rho d phi d theta. Okay, so let's go over an example. Find the volume of a sphere of radius a. So we look at the sphere of radius a. We center the sphere at the origin, and we are going to set up the triple integral, turn it into spherical coordinates, and then we will evaluate. So if you call this sphere E, then the volume of E is going to be triple integral over E of 1 dV. Then we'll switch to spherical. Why do we switch to spherical? Because the region is a sphere and that's easier to deal with in spherical coordinates. Okay, so we're going to turn the integrand write down in the integrand in terms of rho phi theta. Well, the integrand is just 1, so we don't need to do anything with that. dv is rho squared sine phi based on what we just learned, d rho d phi d theta. So that is dv. So this portion is dv. And next thing we're going to do is we are going to set the limits of integration. So what are the limits of integration? Well, rho would go from the origin to this point, and this point is rho equals a. So 0 to a. Phi would go from, well, if you look at a fixed theta, what's the maximum and minimum possible value of phi on top right here, at the bottom right here? So it would be from 0 to pi. And then what are the maximum and minimum values of theta? Well, if you look at the projection onto the xy plane, the projection onto the xy plane is a disk of radius a centered at the origin. So because that's the projection, theta would go from 0 to 2 pi. And this is a pretty easy integral to evaluate. And of course, we know what the volume of the sphere is. So it would be 4/3 pi a cubed. So this would be the volume, but I will let you evaluate this integral. Okay, so we're going to move on to another example. Find the volume of the solid that lies outside of the sphere rho equals 1, inside the sphere rho equals 2. So we have two spheres centered at the origin and above this cone. So we have this cone, we have the z-axis, we have the y-axis and the x-axis. And we are looking at only this portion between the spheres and inside the cone. So this is the solid that we are looking at. So let's call that E. So what is the volume of E? Well, volume of E, as usual, is the triple integral of 1 dV. Then, because we are dealing with spheres and cones, it's best to switch to spherical coordinates. So this would be the triple integral. We'll have to do rho squared sine phi and then d rho d phi d theta. Next, we'll have to set the limits of integration. So when we look at rho, the smallest rho would be on the inner sphere. So inner sphere has radius 1, and the largest rho would be on the outer sphere. So rho would go from 1 to 2. D would go from, so what's the smallest value of phi? It is on the z-axis, and what's the largest value of phi? It is on the cone. So it would go from 0 to the cone. So the cone is z equals root x squared plus y squared. That's what they gave us. So we can write this down as rho cosine of phi, that's z. And this is r. So we can replace that with rho sine of phi. So this gives us tan of phi equals 1, which means phi is pi over 4. So the smallest value of phi is 0, and the largest is pi over 4. And what are the limits of theta? When we project that onto the xy plane, we have regions in all different quadrants. So this would be from 0 to 2 pi. And again, this is not a very difficult integral to evaluate, so I would encourage you to evaluate this one, but it is not very difficult to evaluate. Okay, so we're going to move on to the next one. Evaluate the total mass of a solid whose mass density at any point is equal to the reciprocal of the distance to the xz plane and is positioned inside that sphere. So let's start from the density function. So the mass density is reciprocal, so 1 over the distance to the xz plane. The distance to the xz plane is y. Assuming that y is positive, it would be y. So in fact, it's always 1 over absolute value of y. So if you look at the distance to the xz plane, the distance to the xz plane, this distance, is just the y value. But since y could be negative, it would be 1 over absolute value of y. So that's first finding the distance to the xz plane, which gives us the mass density. Next, we'll have to draw the sphere. So the sphere is x squared plus y squared plus z squared minus 2y plus 1 equals 1. That gives us x squared plus y minus 1 squared plus z squared equals 1. So it is a sphere of radius 1 centered at 0, 1, 1, 0, 1, 0. So it is like this. So this is the solid that they gave us, because they said it is inside this sphere. And if I call this one E, I'll have to find, so the total mass is triple integral over this region of density function dV. So that's the total mass. But y is positive. Why? Because it is never to the left of the xz plane. So now we'll switch to spherical. So what is this equal to? This is equal to, well, first of all, when you do spherical, we'll have to replace the integrand. Integrand is y. Y is r sine theta. So it would be something sine theta. And what was r? R was rho sine phi. So rho sine phi sine theta, that's something that we talked about it earlier at the beginning. So rho sine phi sine theta is y. So it's 1 over that. Then we'll have to multiply by the spherical factor, rho squared sine phi, and then d rho d phi d theta. Next, we'll have to find the limits of integration. So limits of integration, if we fix a ray when theta and phi are fixed, we have to look at a ray. So what is the closest to the origin? It's right here. What is the farthest from the origin? It is right here. So it would be 0. Farthest origin is on this sphere. So if you look at this sphere is x squared plus y squared plus z squared, which is rho squared, equals, so that was the sphere, x squared plus y squared plus z squared equals 2y. So it's 2 rho sine phi sine theta. So this gives us rho equals 2 sine phi sine theta. So this would be 2 sine phi sine theta. So that's the limit of integration. That's the upper limit of integration. Now, what are the limits of phi? So limit of phi would be closest to the origin, the smallest value of angle phi would be here, and the largest would be on the other side. So angles would go from all the way from 0 to pi. And what about theta? For theta, we'll have to look at the projection onto the xy plane. So projection onto the xy plane is a circle based on the y-axis, because if you look at the diagram, the original diagram, we'll see this is the projection onto the xy plane. So it's centered on the y-axis. So it's centered at 0, 1 on the y-axis. So this is the projection. So what are the limits of theta? The limits of theta are from here to here. So 0 to pi. Okay. So this is not particularly difficult to evaluate, but it might be a little bit more difficult than some of the other integrals. So this one and this one cancel, this one and this one cancel, and we get rho. So we have to integrate that, but it would be rho squared over 2. So let's do the calculation. So I'm going to write it down here. So the total mass is going to be integral from 0 to pi, integral from 0 to pi. So here we got rho over sine theta. That's the only thing that is left. Rho over sine theta, the integral becomes rho squared over 2 sine theta. And then we'll have to evaluate that from rho equals 0 to rho equals 2 sine phi sine theta, which is the upper limit of integration. And then d phi d theta. So let's plug it in and see what we get. We get integral from 0 to pi, integral from 0 to pi. When we plug in rho equals 2 sine phi sine theta, we get 4 sine squared phi times sine squared theta divided by 2 sine theta, d phi d theta. Of course, when you plug in rho equals 0, you get 0, so we don't need to write down that one. Now, when we integrate this one with respect to theta, with respect to phi, we'll have to use half angle formula. So this 2 and this cancel, this one and this one also cancel. So we can write this down as integral from 0 to pi, integral from 0 to pi. Sine squared, when we want to evaluate, we'll have to use half angle formula. So we'll do 1 minus cosine of 2 phi, all of that over 2. But there's also a 2 in front, so we can get rid of that. And then times sine of theta d phi d theta. Now let's integrate this and then plug in the endpoints. Let's see what we get. So we're going to get sine of theta is constant. Integral of 1, that's phi. Integral of cosine, that's sine. So that's sine of 2 phi divided by 2. And then we'll have to multiply that by sine of theta. Then from phi equals 0 to phi equals 2 pi d theta. Okay, perfect. So let's now plug in the endpoints. When we plug in 2 pi, we get 2 pi sine of, and this is from 0 to pi, so it is pi here. So when we plug in pi, we get pi minus sine of 2 pi. Sine of 2 pi is 0. When we plug in 0, we also get 0. So that's going to disappear times sine of theta d theta. What is the integral of sine of theta? that is negative cosine of theta. So that's minus pi cosine of theta from 0 to pi. When we plug in pi, we get pi. When we plug in 0, we get negative pi. So that gives us 2 pi. So this is the answer to the problem. So to summarize, this is what we did. We talked about what spherical coordinates are. We talked about the relation between spherical coordinates and Cartesian coordinates. So these 5 formulas are extremely important. You'll have to be able to use them over and over, so you'll have to remember them. When we switch to the spherical coordinates, we graph the solid first. We write down the integrand in terms of rho phi theta. We substitute dv by rho squared sine phi d rho d phi d theta. This is the spherical factor. For the limits of rho, by looking at an arbitrary ray through the origin, we use the closest and farthest points from the origin. These limits may depend on theta and phi. Then we find the maximum and minimum value of phi by looking at the half plane through the origin. These limits may depend on theta. And finally, we find the limits of theta by looking at the projection onto the xy plane. And these limits have to be constant. The spherical coordinates are usually used when we are dealing with cones and spheres. So I will see you in the next video.